Ricart's equation for first order nonlinear equation in the form of ax y prime plus b of x y is equal to c of x y squared plus f of x. Note that without f of x, this Ricart's equation will become the Bernoulli's equation. In Ricart's equation, we let y is equal to y1 plus 1 over phi of x. After that, we take the differentiation, we get dy over dx is equal to dy1 over dx minus d phi over dx over phi of x squared. Then we can get f of x plus p of x y plus q of x y squared is equal to f of x plus p of x times y1 plus q of x y1 squared minus dp over dx over phi of x squared. Then we get p of x y1 minus y plus q of x y1 squared minus y squared is equal to dp over dx over phi of x squared. Then from the first equation, we can replace the y1 minus y by minus 1 over phi of x. Then after we replace it, we get p of x times minus 1 over phi of x plus q of x times y1 minus y times y1 plus y is equal to dphi over dx over phi of x squared. After that, after we replace it, then we multiply all by phi of x squared. Then we can get p of x times minus phi of x plus q of x times phi of minus negative phi of x times y1 plus y1 plus 1 over phi of x is equal to dphi over dx. Then we simplify it and we finally get negative phi of x times p of x plus 2y1 q of x minus q of x is equal to dphi over dx. Treating differential equation as differentiation of a conservative vector field. We know that first order differential equation can be written as p of xy dx plus q of xy dy equal to 0 represents the vector field that is the differentiation of a multivariable function in terms of x and y. In this case, it's possible for us to have two cases. Case number one is the exact form. In the case that the vector field is conservative, it is partial p over partial y is equal to partial q over partial x. Then the pool of solution of the differential equation will be f of xy is equal to some constant. Then the second case is the non-exact form. In the non-exact form, in this case, the vector field is not conservative. Or we can set partial p over partial y is not equal to partial q over partial x. Then, in this case, we need first to find the integrating factor. It can be either mu of x or mu of y, so that we can turn the non-exact differential equation become exact, then we can solve it. Proof of integrating factors. First, we multiply the equation mxy dx plus mxy dy equal to 0 by mu of xy. Then we get mu of xy mxy dx plus mu xy and xy dy equal to 0. Then we take the differentiation. We get d over dy times mu xy m xy equal to d over dx mu xy and xy. Or we can rewritten this as mu y m minus mu x n plus m y minus nx mu equal to 0. Then let's say that mu of x is a function of x only. Then we can get n d mu over dx is equal to my minus nx times mu. Then we move mu to the other to this left side, then n and dx to the other side, and we do separation of variables. Then we can get mu is equal to e to the power of integration of my minus nx over n dx. For the other integrating factor, we let's say that mu of y is a function of y only. Then we get m d mu over dy is equal to nx minus my times mu. Then we do the same thing, we move mu to the other side and m and dy to the other side. Then we do separation of variables. Then we can get the other mu as e to the power of integration of nx minus my over m dy. Example of exact differential equation. So we get 2x plus 3y dx plus 3x plus 2y dy is equal to 0. The first step, we need to check whether this is an exact or non-exact differential equation. The exact differential equation should satisfy partial m over partial y is equal to partial n over partial x. Then after we calculate it, partial m over partial y is equal to 3 and partial n over partial x is also 3. Then we know this is an exact question, the exact differential equation. Then we need to take the integration of the fx dx. Then we get integration of 2x plus 3y dx. After we integrate it, we get x squared plus 3yx plus h of y. After that, we differentiate this in respect to y. Then we get 3x plus dh over dy. Then we notice that the 3x plus dh over dy should be the same like 3x plus 2y. So we know that the dh over dy will be equal to 2y. Then after that, we want to know what is h. Then we just take the integration of 2y. We get y squared plus c. Therefore, we know that fxy is equal to x squared plus 3yx plus y squared plus c. Example of the non-exact differential equation. So we got y dx plus 2x minus y e to the power of y dy equal to 0. So the first step, we need to check whether this is an exact or non-exact differential equation. Then we need to check whether partial m over partial y is equal to partial n over partial x. After calculating it, we get that partial m over partial y is equal to 1 and partial n over partial x is equal to 2. and 1 is not equal to 2, then this is a non-exact differential equation. Therefore, we need to find the integrating factor of this differential equation. So first we get m is equal to y, and my is equal to 1, and n is equal to 2x minus y e to the power of y, and nx is equal to 2. In this case, to find the integrating factor, we need to be careful in choosing the mu x and the mu y. So in this question, if we put mu x to be our integrating factor, we will see in the integration of in the denominator there will be 2x minus y e to the power of y, which is impossible to integrate it in respect to dx since there is variable x and y. So therefore in this case we need to choose mu of y as our integrating factor. Then we get mu of y is equal to e integration to the power of integration of minus 1 plus 2 over y dy. Then we get ln e to the power of ln y. Then we get our integrating factor as y. After we get the integrating factor, then we multiply it to our original equation. So our original equation multiplied by y will become y squared dx plus 2xy minus y squared e to the power of y dy equal to 0. Then now when we check the partial m over partial y is equal to 2y, and the partial n over partial x is also equal to 2y, then now we get that this already turned from non-exact differential equation to exact differential equation since it's equal. So then next step, we take the integration of y squared dx. We get x y squared plus h of y. After that, we take the differentiation in respect to y. We get 2xy plus dh over dy. Then we need to, because since we integrated, we differentiated in respect to y, then the 2xy plus dh over dy should be equal to 2xy minus y squared e to the power of y. Then dh over dy should equal to minus y squared e to the power of y. Then h will be, we integrate both sides, so h will be equal to negative integration of y squared e to the power of y. And we calculate integral, and we get h is equal to minus e to the power of y times y squared minus 2y plus 2 plus c. After we get the h, we put it back to the equation, so we get f of xy is equal to xy squared minus e to the power of y times y squared minus 2y plus 2 plus c.
That is the end of our presentation. Thank you for watching.